introduction. Thank you, Nina. So Nina is a co-founder of YosysHQ, a company that works on improving the Yosys open source EDA tools and providing related services, and she's part of the FDF team as well.
Yes. Thank you. Can you hear me? Does it work well?
Maybe a bit closer can be.
Closer. Yeah, I think it floats over sometimes. Is it better now? Or even closer?
What do people think? I can hear. Okay,
yeah,
good.
Thank you. All right, so yeah, I was told yesterday I need to give a talk. And so I resurrected talk that I gave, or that we gave at ISA a few months ago. So for bonus challenge mode, these are not my slides and this is not my work. I was only supervising it. So I guess this is now the quiz, the pop quiz of how much attention I pay to what my engineers do. So basically, this is about some work we did for the ESA, where we implemented support for the NanoXplore NG-Ultra FPGA. And so this is kind of a talk that also takes this as an opportunity to explain a little bit what in general is involved in adding support for a new architecture to our open source tools. So first up, I'll just introduce a little bit what we actually do at Yosys, and so what are our tools. Mainly here, the relevant ones is Yosys, which is the first tool and the one that our company is named after. So this is a synthesis tool, open source. Started out at the very beginning with mostly interest in the lattice ICE40 FPGA, and that was kind of the goal for a lot of hobbyist people to just get an open source toolchain for one of these very small FPGAs that you can get maybe for 10, 20 euros that is accessible to anyone. And so it kind of grew out of that. You can do now synthesis for both FPGA and ASIC in a fairly generic manner. It's also become more and more useful for other things beyond that, just because you can manipulate netlists in general. So for example, the other tools that are not really relevant today, but which we built on top of that is like formal verification tooling, which I talked about last year, by the way. We have an equivalence checking tool. We have a mutation coverage tool. All of this is just because we can manipulate netlists in some way and export it to various formats. The other tool we have, which is nextpnr, is the place and route tool. This is the central part that will be presented here today. So this is a fairly generic place and route tool. It takes as input a JSON netlist format that Yosys can export. And yeah, I guess the more details will be in the later slides then. But first, just maybe most of you probably, I've heard, are working with Xilinx cards. And so maybe you have not really had the opportunity or need to work with any open source synthesis and place and route tooling. So maybe a little bit of what are the pros and cons for each of those. So on the synthesis side, the pro of having an open source tool is kind of, well, you have a generic tool that can be targeting many architectures, so you have a lot less compatibility issues switching between one and the other FPGA, as long as all of them are supported by the tool, of course. And it's also very scripting oriented, and so it's a little bit easier to integrate with other tools. Works a lot better with makefiles than the vendor tools generally. And because it's open source and you have all of the intermediate steps in the synthesis are kind of exposed via scripting, you can do a lot more fine-tuning or like changing how you want to synthesize your design. That's especially interesting in research usually. And also, if you want to work on adding some custom features inside the flow, you cannot really say, oh, I want to use Vivado, but I want to change how I implement my DSP or something like that, right? But with Yosys, you can, because it's all open source. And also, of course, there are other open source projects that build on top of it. So like Litex and Amaranth, they have all these facilities for integrating with this. The downside is, well, we have not as much resources, I guess, as the vendors, of course. We just have like a dozen people in total. So the first point here is actually no longer true. For system Verilog support, there is now a Slang Yosys plugin that does quite a good job for most of system Verilog is now really well supported, except SVA. SVA is still missing. But for synthesis, this is now actually working pretty well. And of course, for VHDL, we have, thanks to Tristan, the GHDL plugin in Yosys, so that is also working quite well. The downside is also that our tools are not quite as well optimized, and especially well optimized for the architecture than the vendor tools. And also, because we have this very clear tool split between the synthesis is one tool and the place and route is another tool, there isn't really any integration. And also, we don't have resource limit implementation. So the synthesis tool doesn't actually know how many block RAMs does this FPGA have, and it has to kind of guess how many can it use. This is one of the downsides. For place and route, same kind of advantages in a way and disadvantages. You have something generic. You can integrate with research. You can pick something up. And you also have much finer control, again, about how do you want to place. So this kind of depends. Some vendor tools have better ways of targeting that. But the NanoXplore in particular are really bad in terms of what they offer you. You can only say you want to place this in this general area. That is the overall kind of control you have about placement. But you cannot target, I want this slot in this specific place. That's just not available. And yeah, on the downside, again, for nextpnr, the problem is that mostly what people have implemented is the FPGAs that they were able to access and reverse engineer themselves. So we have a lot of support for ICE40, ECP5, the small FPGAs. Somebody added the Go and Little B. But usually nobody is a hobbyist who can afford to get this 20K FPGA from NanoXplore that is like radiation-hardened for space applications. There aren't really many hobbyists that have access to this and can go work on this. So it was quite an interesting opportunity that we got to work on this with ESA this time. But yeah, also in terms of optimization, because everything is generic, it's not usually quite as able to get the performance on the specific architectures. The last point that we need in our toolchain, of course, is the bitstream manipulation. And there, this one is kind of one you have to re-implement really for every FPGA. There isn't anything generic that can be done here. So you need it kind of if you really want to offer a full open source flow. But then the vendors usually don't want you to have this. So it's a lot of work if you want to reverse engineer it manually. And yeah, you can make people unhappy if you do this. So what does it actually look like to implement a flow? So in this case, it was also a very interesting thing because this FPGA is quite different in architecture from what the other FPGAs that we are used to working with. So on the one hand, it's quite larger. This one is a 500K LUT. Usually the FPGAs in the 10 to 100 euro range, they kind of have maybe 10K, 20K, somewhere in that area. The structure of the FPGA itself is also very different. So they have these tiles, which are kind of similar to slices, but the tile has, I have to remember again, about 200 LUT in it, something like this, if I remember correctly. So it's very huge compared to when you have a slice. Normally, I think you have 4, 8, maybe 16 on other FPGAs. So this also meant that the routing is quite difficult. So they have these tiles are interconnected with the crossbars locally. But then the routing became so it's quite unusual, but also I think under-provisioned overall. In general, what does it look like if you want to add support for a new architecture to our toolchain? First up, you have to get familiar with the architecture. You look at all the documentation you have, what are your primitives, what you have to work with, essentially. Then you first need to add support for synthesis in Yosys so that you can have a netlist. So there, I think there's a slide further down to go a bit more into detail of what's needed there. But generally, there is, the basic stuff for LUTs and flip-flops is quite generic. Then you have memory, DSP, and so on, where you need to map the hard blocks. That gets a bit more difficult. And then for place and route, there are then several parts. So first, you have to kind of internally for the tool describe what does the architecture look like. This is called the chip database. So there you have the primitives. So you need to know what are kind of the actual little pieces of logic you have in the FPGA, and then you need the routing graph, which says what are all the possible connections and which of them are programmable and so on between all the points in the FPGA. Then you need to manipulate the bitstream, so you need to figure out how to reverse engineer the bitstream usually, and then because you need to also verify and so on, you usually have the packing and unpacking things that you want to do, also for verification to make sure you didn't make any mistakes. And then inside nextpnr, the routing and the placement algorithms are generic, so technically with the chip database it should just work, but generally you need to do a little bit of architecture-specific preparation, and so we have packing things, or you maybe do some pre-placement or pre-routing of some things that are maybe better done by hand. So for example, if you only have 4 PLLs, you don't want a generic placement algorithm for the PLLs, you can usually do something a bit more intelligent there. So there's a little bit of pre and post-processing usually done on the nextpnr side. So in this project in particular, the synthesis was not really the main goal. We happened to do it anyway because we needed it for debugging purposes, but the idea was that we take the synthesis that exists from the vendor, we just work on the place and route part. We didn't have to do any, or we weren't supposed to do any reverse engineering. We got provided the data about the primitive descriptions in a bit more detail than you get from the documentation from the vendor. We worked together with NanoXplore on this. But also we were not supposed to make our own bitstreams, so then NanoXplore had to implement an interface for us to give them back the placed and routed netlist for them to generate the bitstream for us. So this is what the flow looked like in the end. We had the 2 versions, so either you could use, this is the bottom view, you can use impulse for synthesis, then that can already export the Verilog or VHDL, but in this case Verilog is the useful one for us, netlist, the synthesized netlist. This is usually the post-synthesis netlist that you can use for simulation, but we can also use it to import into Yosys, and then Yosys just translates that into the JSON format that nextpnr can read. Or alternatively, the top way is if you use the kind of not quite fully implemented synthesis flow that we have, you can also directly synthesize in Yosys from the original RTL to the JSON netlist. So then this JSON netlist goes into nextpnr, nextpnr places and routes it, and then exports this JSON bitstream format that then inputs the NanoXplore added an interface to their tool to be able to import this JSON bitstream and transform that into the binary bitstream that you can actually load on the FPGA. So going back to our steps, what was it like to familiarize ourselves with the architecture? So here we have to go basically through all the documentation, and then usually the vendor documentation you can actually find on the website. It kind of lies to you. It's a simplified version of the primitives. It doesn't actually represent quite what is on the actual hardware, so then you go back to them and you ask them more questions, and they tell you, oh yeah, actually this one port internally is like 3 ports, and we treat it like this, and so there was a little bit of back and forth with them. Then we have to buy a board and play around with it, create some small examples and test out like what does this look like if we implement it, and then use the visualization tools and check exactly what's going on. By the way, one easy way you can crash a lot of hardware toolchains is you create a design, and the only thing it contains is a simple wire that connects one input port to one output port, and that has 0 cells in it, 0 LUTs. Most tools do not know how to deal with this, and they will just crash. So then, first step, you add also some Yosys support. By the way, we support this design that has only 1 wire. So I think I briefly mentioned this earlier. We have quite generic ways of handling LUTs and flip-flops because basically these are the same in every FPGA. So you have to tell it, okay, I have LUTs that have 4 inputs, 6 inputs, whatever. So the NG-Ultra uses 4 input LUTs. And then you tell it, okay, this is the name of the primitive. And here you map it. So you have the generic LUT, basically you map it to the specific LUT. For flip-flop, it's quite similar as well. We have internally, we have an internal model that has basically all the combinations of reset, synchronous, asynchronous, enable. You have the initialization. It can be 0 initialized, 1 initialized. You can't actually initialize it. All of these combinations are available internally. And there is some mechanism where you can just tell it, I have available on this architecture this subset of actual flip-flop styles, and then it just synthesizes it down to that subset, and then you just tell it, okay, and this is the actual name of the primitive, and it outputs that. So there we then, of course, have to double check that we did it right. We do some equivalence checking, and we then put this, export this to Verilog, put it in the vendor tool, make sure that one accepts it. And then this is where drawing the rest of the OL comes in. So the latent flip-flop is quite easy. You can usually do an acceptable job of that within a few days. Then you have all the hard blocks that are in the FPGA. Those usually differ more and more. So carry chains, usually not too different, although these are also a little bit interesting in the NG-Ultra. Block RAM, we have some format where you can describe what is the shape of the block RAM, but these are also usually not too many degrees of freedom, although we had a little bit of a surprise here that this is not power of 2 in size. DSP, that is the one that's usually quite difficult because it's the problem is a different one because you have to recognize a group of cells in the original netlist and combine all of those into one primitive, whereas all of the other problems are usually you recognize one thing in the original design and you map it to a group of primitives. So taking one thing and breaking it up into multiple is very easy. Finding a pattern in a graph and extracting it into one thing, this is an NP-complete problem actually. Although in practice it's not quite that difficult, but it's still more difficult than the rest. So implementing the DSP is usually about as much work, if not more, than the rest of of supporting the architecture. So this part we didn't do in this case, so you can only manually instantiate the DSP right now. Then going on to nextpnr, creating the chip database. We got routing information from the vendor. We had to create scripts to extract that, create more, then to create the chip database. And then we have a lot of the pre-processing kind of steps that we do that are architecture specific. So one thing we commonly do in a lot of architectures is that we group, if we have a flip-flop and the LUT that is feeding into that flip-flop, we group those into one functional element so that it can be placed together because there is usually not much choice here. It doesn't make sense to start exploring where do I put this LUT that feeds into the flip-flop. Obviously, you want to put it right where the flip-flop is. So we do that already ahead of time. We pack all of these together so that they get just less elements for the placer to decide where to place. And then all of the special things. So here the CSC, SCC, this is basically the low skew network. So for routing mostly, for clocking, sorry. We have a special clocking network, and then you just decide where do you promote signals to the clock network and back to logic. So then on the routing side, you have also optimization. So LUT permutation is just if you decide on routing that actually using this port on the LUT to go here is actually much better than what the synthesis tool decided it's going to connect on the first port, because you can just rewrite the LUT table on the fly afterwards. We give the router the choice to go to any of the ports, just whatever is most convenient to it. And then we rewrite the LUT table after the fact to reflect what it actually chose as input that makes the most sense for the routing to have the best timing. And yeah, similar problems for clocking and so on. Then for bit streaming here, we didn't do much of that, so we had the output for the JSON format. There we would normally have some mapping where we decide each of the kind of the decision to place this LUT in this place and comes out to this type of configuration bits that go in this place and so on. And often we have this for the ICE40, for example. We have then the back conversion that you can take a finished bit stream, you can convert it back into Verilog and then use it for validation. So this is where the quizzing comes in. So overall, this combines into this flow where we load the netlist, we then pack into the components together, we give it to the placer, we let the placer run, we give it to the router, we let the router run, and then we export it back to the bitstream, in this case in the JSON format. The placement and routing algorithms are generic and built on an architecture API, so we have to make sure that we describe the chip database in this, to match this API, for this we have a special Python language which allows you to generate this, which is called Himbechel. So there you can like, programmatically generate the architecture description with that. I think the packing and this I've already described. I don't need to go over it again. I don't know much more about it anyway. So yeah, then you basically do the packing. You have the pre-placement of the things that you know where to place. So for IOs, you already have a location, so you just put them there. You don't let this be done generically. Then we have some post-placement treatments. So basically, the things that are not quite generic, you have to do after the fact and fix it. And then post-routing, which I mentioned, the recalculating the LUT tables and so on. And we had some extra fixes we needed to do also for the crossbar configurations in this FPGA specifically, because the routing is so different. We ended up, the router ended up sometimes deciding to go take the same signal and enter twice into the same crossbar. For I think the timing that we got wasn't quite right, and so it decided that was the fastest way to do it. But the vendor tools didn't like that at all, so we had to just fix that up after the fact to make sure that didn't happen. So yeah, in conclusion, I think as a user, what are the advantages of having an open source tool? Well, our tools are definitely smaller than the vendors. Even the ePhoenix tools are much bigger than ours. So everything is open source. You can look at all that is happening. Our tools are also, if your designs are not too large, they're usually faster. On the very big FPGAs, we sometimes struggle a bit more than the vendor tools. But overall, you generally can iterate faster. Things are more portable if you have always the same tool reading the sources. And you can also test, is your design understood the same way by this other tool as the vendor tool? Like, if you have any differences between how the tools understand your source code, generally that is an indicator that your source code is maybe ambiguous. So I suspect that this is more of a problem in Verilog than in VHDL, but in Verilog it can be quite a thing. So yeah, as a vendor, it's also an option to use our tools instead of making your own. So we have the Cologne chip who have taken advantage of this option. So we are now also a vendor tool, I guess. But yeah, just in summary, what did we end up making in this project as the final state of our prototype? So we only support the NG-Ultra. There is an Ultra 300, which is the same architecture, smaller chip, but we didn't get access to the hardware, so we didn't implement that one. We have NG medium and NG large as placeholders in our synthesis flow, just because the primitives are mostly called the same, so it was mostly there. The blockgram mapping is not optimized in synthesis. The DSP mapping is not implemented. For DSP instantiation, we didn't add all of the wrappers that the vendor has. So there's like different names for the primitive just for different configurations of the DSPs that all then map to the same DSP underneath. We didn't add all of those, and we don't have full simulation models because those were encrypted. We don't get them, so we would have to rewrite them ourselves. We didn't do that. In nextpnr, you can place and route designs, usually not too far off from impulse, although when it gets like more to the limits, we struggle a little bit more with the borderline designs. So we definitely don't have the performance of the vendor tools. We found that the placement is really, really important on this FPGA more than anywhere of the other FPGAs, because the routing is so under-provisioned that it has a big effect if you suboptimally place something. We don't have some of the features of the FPGA, like the high-speed I/O, and this is actually also an FPGA that has an embedded ARM core, so we don't have support for talking to that either. So we would definitely like to do a follow-up project on this to kind of round out the support more. So thank you very much for your attention. If you have any questions.
Thank you, Nina. Any questions? Okay. Mm-hmm.
It's more a comment than a question, but I know at least one person who is using your tool on the arm of a SOC, of a Xilinx SOC, just to compile everything locally and generating the bitstream locally.
Yes, yes.
So this is possible. And he claims that okay, it's much slower than using a PC, but you don't have to do transfers of files or whatever, and it's actually something comfortable. So I don't know yet. Yeah, just a comment.
Sorry, so it's an FPGA compiling FPGA software for itself. Okay,
Yeah,
scary.
I think there was even someone who once did this with partial reconfiguration in a softcore. Like you have a softcore on the chip. So I think partial reconfiguration is only supported on like the ECP5 or something.
Oh, yeah.
So it's very limited in where you can do it. But so you have the softcore on the FPGA, and it is running the tool to compile the partial reconfiguration bitstream for the other piece of the FPGA that it's currently running on, so it can reconfigure itself.
Any more questions, comment? Yes.
Sí. Hi, thank you for your presentation. We are in part of the company in the university. We are working with NanoXplore, but not with the Ultra, with the Medium. Are you making something with that board?
No, so we don't have the board. So all we have is kind of a stub for the synthesis part, but the synthesis part only. So
Okay.
Probably not all that interesting. So basically, if you have a design and you only want LUTs and flip-flops, but you're very particular about how you want your LUTs and flip-flops, maybe you can use our tools.
I have a question, more general. So I was looking at the website, and some companies gave you so you can support some FPGAs. So they basically opened up how to do the place and route for them, and some didn't. What do you think? So what is the drive for a company to let you do that, and why others, the bigger ones, don't?
So I think the ones that are working with us, they're usually very small, just starting out, and they don't want to have to rewrite their own toolchain, because it is a lot of work, right? And there's one that already works, and adapting that is much less work. And so I think for them, they probably get more quicker than they would get if they started from scratch, writing their own toolchain. Whereas for the big ones, they already have their toolchain. There's no good reason for them to have another toolchain in the end that works less good than what they've invested the last 20 years building.
Yeah, so basically, if this model is correct, there's never, like the big FPGAs would never have a real reason to.
Well, I mean, if there is enough acceptance among the others that they start saying, okay, well, this is a common, like you would have a compiler, you have LLVM now is basically the compiler for everyone. And if you make a new architecture, of course, you're going to use LLVM. You're not going to make your custom compiler just for your
that's a good point.
your CPU, right? So if we can get enough traction, we could go to that point, right, in some time. I don't know if we, how to get there, I'm not sure. But I think we are moving a little bit in that direction already. So there's chances that we can get there. And also, I mean, even for the big ones in the end, at some point they are not selling the tools, right? The tools for them are just a cost factor that they have to do so that they can sell their hardware.
Yeah.
So if they can save money there, if we can make an argument that this can get good enough that they can save money in the future, I think that could be attractive.
Yeah, and that shows in the quality of the tools. I think I speak for everyone here. Any final question? Otherwise, we can. Oh, yeah, Rui.
Yes, because I see as a user, you mentioned one bullet point. You said it's a faster iteration of the full workflow. I guess what are you comparing to? Why is it faster?
So in this case, in particular, for the NanoXplore tools, if you're working with maybe not your full design that occupies the full FPGA, but you're working maybe on one IP core and you want to test just that one, So if we, for example, take the I think we have one of the LiteX examples that we always use. So for that one, the time it takes for Yosys and nextpnr to do synthesis and place and route is less time than it takes for the NanoXplore tool to boot up so that we can generate the bitstream.
Wow. Wait, do you have like the speed, like the full, all the way to bitstream, I mean, for that particular case?
So this one is a very small design, but so
Okay.
it takes about, I think it was
It's a quiz.
5 seconds or something to do the synthesis and place and route, and then like I think 1.5 minutes to do the bitstream generation in the impulse tool.
Thanks.
Okay, thank you, Nina. Let's thank Nina again.